Okay, so today we are continuing the topic on solving the Cauchy's problem for the ordinary differential equations, and the topic of today's class is stability. So we are still in the chapter number 4, ordinary differential equations, Cauchy's problem. And last time the paragraph was number 6, if I'm not mistaken. Oh, I'm sorry. The paragraph last time was number 6, so today we have number 7. Stability. Stability of numerical schemes for solving Cauchy's problem for the ordinary differential equations. Hello, Cherascon. Are you here? Can you hear me well?
Hello, Professor. I'm here.
Well, but I cannot hear you very well. The sound level seems to be very low. So if you want to ask a question, you will need to speak up. And probably I forgot to share my screen, so I need to share my screen to let you see the board. Okay, so can you see the board?
Yes, I can see.
Okay, so today's topic is stability of the numerical schemes that we use to solve Cauchy's problem for the ordinary differential equations. And as usual, let's start from writing the system, or not the system, but a single equation that we are considering. So at time from t0 to t capital, and we have an initial condition at time t0. This is our original problem star. And recalling some theory of the ordinary differential equations, there was a definition of stability. I don't remember if I gave you the definition of stability of the solution in this set of lectures. Do you remember, Alexandra? How the stability of the differential problem is defined?
No.
Okay, so the definition is following. The solution of the problem star is called stable. Solution of problem star is stable if is stable with respect to the initial conditions stability with respect to the initial conditions if for a disturbed initial condition U0 star, which can be defined as the original initial condition plus some small variation, some small disturbance, the following holds. Holds true. The solution of the original problem minus the solution of the disturbed problem is bounded by some constant k capital, which may depend on the length of the interval that we are considering, multiplied by the norm of the difference between the original initial condition and the disturbed initial condition. Hello, Wang. Nice to see you. So, what this definition says, let's discuss what it actually means.
So we just took another initial conditions and repeat the algorithm.
We slightly disturbed our initial condition, and this is what happens all the time. We are solving our problem this way or another, because nobody can measure temperatures exactly. Nobody can say what is the concentration of a species in the starting moment of time exactly. This is the physics or laboratory cause of the disturbance, and another cause of the disturbance is the finite accuracy arithmetics that we are dealing with when we are solving any problem on a computer. So if we have an exact number u0 and we write down this number into computer memory, you already know that we always introduce some error. This can be considered as error delta, and we need to understand what will happen with our exact solution of a different problem. It's going to be a different problem, not the star, but some problem star asterisk, for example, or star. You may denote it however you want. But if the solution of this disturbed problem will be too far from the solution of the original problem, you can intuitively feel that it's a bad thing. It means that the differential problem itself is not formulated in a stable way. And this constant in the theory of differential equations, this constant is defined like this. Exponent. It should be an exponent of the following integral. F, derivative of function f by its second argument. This is how this constant k of t is defined. So you see that it's a quantity that depends on the length of the interval. It may depend on the length of the interval, depending on how the right-hand side of our problem looks. And another thing you can see from this relation is that this integral goes under the exponent, which means that if this integral is positive, right? If this integral is positive, whenever you increase the length of the interval, whenever you want to know your solution on a longer and longer periods of time, this quantity will grow, and it will grow exponentially, very quickly. It may grow very quickly, right? So for the problems with the positive derivative of the right-hand side by its second argument, we should expect some variation of our solution that we don't like, but we cannot do anything with that. This is the original formulation of the original problem. We have to deal with this somehow. For example, we can restrict ourselves to consider shorter periods of time. And then after this period of time has elapsed, we need another piece of information from the laboratory or from the process to correct our solution at this new moment of time, right? So we cannot predict forever. On the other hand, if the right-hand side is such that the derivative by its second argument is negative, then this is a good thing for us as numerical mathematicians at this moment, right? Because this quantity is decreasing with time. And we can be sure that this relation is defines a pretty good solution U star that is coming closer and closer to the actual solution as the time evolves. Okay.
So if k is too big, we can't use this stability expression because we know that our ALK algorithm for this period of time is not stable.
I'm not speaking about the algorithm for the numerical solution of the problem at this point of time. I'm only speaking about the properties of the differential problem itself. It's pure discussion of the differential problem properties, not the discussion of our methods, right? And the next step we need to do is to move on and introduce our method and see how the method improves or makes the problem even harder, right? Because the method can introduce another source of instability. We need to request that our method at least doesn't spoil the stability properties of the original problem. Doesn't spoil the original stability characteristics of the problem. Okay, so we discussed this. This, so to say, constant, it is a function actually of the t capital, but if the interval is fixed, then it's going to be a constant. This constant plays a role of a condition number for our differential problem. What it means. Even this inequality holds true, but the constant is very big. It's not a good thing either. Do you feel it? That you have this relation, but this guy is very large.
Yes, so when the right-hand side is too big, this condition is what?
If in case this k capital is a large value, even for very small variation, very small disturbance in the initial data, you may expect very large difference between the disturbed solution and undisturbed solution. That's why having a big condition number is bad. Okay. Let's hope that our k is relatively small. Ideally, it should be in the vicinity of 1. Unity is what we like here, right? Yes, choose one.
Here you can choose kxt as an exponent function. Can we choose any other function like logarithmic and any other?
Cherascon, it's not a matter of choice. It is a reality. It can be derived, and it is derived in the theory of ordinary differential equations. I'm not deriving it here on the board because we are talking about numerical methods, not the mathematics of ordinary differential equations. But it's not a matter of choice. It's fact. It's a fact.
Okay.
This is how k depends on the right-hand side of our problem. Okay, hope I answered your question, and then let's continue. So let us now. This was item number 1. Let's go on to the item number 2. Let us consider a general form of a k-step numerical method. We discussed several of them already, like Euler's method, several flavors of Euler's method. We discussed Runge-Kutta methods, and we briefly touched base on the Adams-Bashforth methods, right? Last time. And I hope you remember from the last lecture that the general form of the method can be expressed like this. This is the approximation of the left-hand side of our equation, actually. This represents the finite difference approximation of this derivative. This approximation may be very different. K may be equal to 1, or k may be equal to some number larger than 1. And in all those cases, you get different finite difference formulas to approximate this derivative. But the idea is the same. It is just an approximation of the derivative. And on the right-hand side, you have some function phi capital, which depends on the right-hand side of the original equation. It involves time, it involves yn plus 1 minus j, and so on, yn plus yn, and then yn plus 1, and it also depends on the time step that we chose for our scheme. We've written this formula last time. Okay, so let us say that this is our numerical method, and since this is a k-step method, in general case, this method requires k initial conditions. K initial conditions. Let's denote them by y0, y1. I should denote them somehow in a way. Okay, that's fine. Y, k. These are exact initial conditions. We discussed last time that only this guy is known from the original problem, right? Do you remember the discussion?
Yes.
Only this guy is known right away. It is equal to u0. And the other guys can be obtained. How can they be obtained?
For example,
By Euler's method, or by a better approach is to use some higher order Runge-Kutta method. So we need to decide how to get these values, but we can get them. We know some options to do that. Let's imagine that we have introduced a disturbance in each initial value that we have here. Let's say that y0 star is y0 plus delta 0, some delta 0, and so on. So this is how we get a disturbed numerical solution. So if y defines the exact solution of corresponding to this scheme, 2 stars, then after introduction of disturbed initial conditions, we will get another scheme, we can say that, like another scheme, which gives us a disturbed solution, y star. And the question that we want to be able to answer is how far this disturbed solution is from the original exact solution of this difference equation. How large is this norm? This is what we are interested in. right? And we want this norm to be as small as possible. At least we want that this norm is bounded by what? By the norm. How should I denote the initial conditions? By delta, actually. I can just write delta here. Considering delta as a vector, delta is a vector composed of delta 0, delta 1, and so on, delta k minus 1.
But why isn't it vector?
So you can combine all these individual contributions, individual disturbances into a vector.
The final function is not left. So
It is a vector because it what sits behind the letter y? It is a whole set of values for j from 0 to n capital. When we formulate this method, we usually introduce a mesh on our interval from t0 to t. And this is t0, and this is called tn, t1, t2, and so on. Do you remember?
yes, so it's like a shift.
I'm not sure I understand what you mean by shift. Why shift?
I mean that for delta, for example, delta 0 corresponds to some y.
Delta 0 is a small disturbance that is introduced to the initial condition at time moment t0. Delta 1 is a small disturbance
In this equation,
here,
yeah.
inequality, yeah. Delta is a norm of a vector composed of all disturbances that were introduced in all initial conditions.
So like a sum.
Yes, we can discuss a particular form for this norm, how this norm can be calculated, but you can think of this norm operator as a maximum of the absolute value. I will write it down instead of saying it. From 0 to n. This, you can consider this norm, for example, corresponding to this formula. So it's going to be a maximum norm. You can also consider a Euclidean norm, which is square root from the sum of squares of all the components, component differences actually. Okay. It doesn't matter which particular norm you will take here. Okay, an important thing here is that here some constant k capital should sit as well, parallel to the definition for the original problem. But this k capital will also depend on the time step that we chose for our numerical scheme. It should depend on the length of the interval. No way to make it independent of the length of the interval, because the original problem depended on the length, right? But the dependence on this tau is something we don't like. Why? Why we don't like the dependence on tau?
Just we don't know the tau.
Well, we know tau, we choose it. Every time we start solving the problem star numerically, we have to choose tau.
Yeah.
So that we know tau, but if it happens that this function k depends on tau in a such way that in such a way that for any fixed t capital and tau tending to 0, this constant tends to plus infinity,
Yes.
it can happen if we constructed our numerical scheme inappropriately.
Yes.
Theoretically, it can happen. In this case, this relation will not guarantee that the numerical solution of the disturbed problem is close to the numerical solution of the original differential problem. Okay? So this we don't like.
You mean that it's like
This shouldn't happen, actually. Okay? That's why we will define stability of the numerical solution as follows. Well, I will delete the original problem. Hopefully, I hope everyone remembers it already. And I will keep this for a moment. Definition of the stability of the numerical scheme. The numerical scheme, 2 stars, is called stable if this inequality holds true with some constant k dash, which does not depend on tau.
I think when tau goes to 0, k should go to 1. No?
We need to work hard to make this happen.
No, but I mean, I'm about this. It should not happen. Tau goes to 0.
This is my wish. I don't want that my scheme is formulated in such a way that this constant tends to infinity when tau tends to 0. I can formulate the scheme in such a way.
So it's not about the formula k to the power of tau.
No, it's not a power. I'm sorry. Probably I'm misleading you. Let us write it this way. Maybe it's gonna be better, more clearer for your understanding.
In this case.
I just want to stress that it's possible that this k depends on tau small, on tau, if we were not accurate in defining our numerical scheme.
So it's just it will have this. It's just a situation of it, just a choice. It will.
Yes.
It's possible, but
It's not just a choice. It's a work for us to formulate the scheme in such a way that this constant for this particular scheme does not depend on tau. This is what we need to ensure when we formulate our scheme. Okay, so we define the stability of the numerical problem, and now you see that it is pretty parallel to the stability definition for the original problem, right? So k here depends only on t. It means that if this definition holds true for our particular scheme, then our scheme does not spoil the stability properties of the original problem. At least it doesn't spoil the original problem stability. And this is good. Okay, let's discuss what conditions let us say that this definition holds true. Actually, proving that this holds true for any for an arbitrary right-hand side of our problem. Just repeating problem star for the reference. So, to prove that this holds true for any f, taking some particular form of the method is a problem that's not solved so far, and probably cannot be solved for any undefined right-hand side. Since this problem is very hard, in 1950s, Swedish scientist Dahlquist proposed the following approach. Let us take a set of counterexamples, so to say. Let us take some particular forms of this right-hand side that we think are representative of the most problems or the most important problems that we are dealing with. So you see the point? We are not trying to prove this fact for a particular scheme for any f, but we take a particular form of this f and prove that this definition holds true for our particular scheme for this particular f,
So
at least.
So for a particular f, prove that k doesn't depend on time.
Yes. And we take such counterexamples that can us say if our numerical scheme doesn't satisfy this definition even for the simplified f, we can say that there's no point in considering such scheme. So it's like a sieve for the schemes, theta. We just throw away those schemes that do not satisfy even simplified conditions for simplified problems, right? And the first simplified problem that he proposed to consider was f is equal to 0 everywhere. Just 0. Why? Why he proposed to do that? In case f is 0, what is the solution of the problem? How it looks like? What it looks like?
0?
No, it's not 0, it's constant.
Yeah, no, yes.
It's some constant, which actually means which is actually equal to this u0, right? Because otherwise this constant cannot satisfy the initial condition. The only way it satisfies it is equal to the initial condition. So if the scheme is so bad that it cannot preserve this property for the simplest problem, we can say up front that there is no point in considering such a scheme, right? If it cannot ensure that the constant solution remains constant solution forever, the scheme is bad, definitely, right? So, let's call it definition number 2. Definition number 3. The scheme 2 stars is called zero stable. По-русски нуль устойчивый. Zero stable. If the relation 3 stars, if 3 stars is true for this scheme when the problem star it has f equal to 0. Okay, if we take such a problem with 0 right hand side and we prove that our scheme satisfies this relation, then we say that the scheme is zero stable. And this is the property that we want from every scheme we work with. The minimal stability property. Now it is important to formulate some algorithm of checking. We need to be able to check when a scheme is zero stable or a scheme is not zero stable. So let's write our scheme. Let's rewrite our general form 2 stars for this particular case when f is equal to 0. How it's going to look. When f is equal to 0, then 2 stars will look like what? The right hand side will disappear, right? Because it only depends on f small, and since f small is exactly 0, then phi disappears. Phi capital disappears. And we only have the left hand side n plus 1 plus alpha 1 yn plus 1 minus 1 plus and so on plus alpha k yn plus 1 minus k is equal to 0. This is the differential equation. It's not differential, finite difference equation. In addition to this equation, we also have, as usual, a set of initial conditions. Right? So this equation is defined for any n, from 0 to n, or maybe better to say from k to n. Do you follow?
So why it doesn't have time?
This is our numerical scheme that approximates the original problem star. Okay? This scheme approximates the derivative using a finite difference relation. These are some coefficients that define a particular scheme that we are using, some numbers. And these are the values of our unknown function at the points of the time mesh. Okay, at some moments of time. And we are saying that since there is no right hand side, the scheme will look like this. It is an equation that depends on n, right? And this equation is true for every n from k small to n capital. in every point of our mesh after the first k points. Okay, and for the first k points we have initial conditions. Right? So we formulated this guy. I have to delete it, although I want ideally to keep it on the board, but unfortunately I have no space. So there is a theory of this type of equations. It is called the finite difference equations theory, and it's possible to discuss the basic facts of this theory during several lectures. I don't want to spend so much time. I just need some facts from this theory. This equation is considered like parallel to a differential equation, since this sum, this linear combination of unknown function values, approximates the derivative of our original equation. This equation can be considered as an approximation of the ordinary equation, and it is an approximation, and the theory is very similar. Theory of such equations is very similar to the theory of ordinary differential equations. And the next step we are going to do is we are going to define or try to search the solution in the following form, parallel to how we do it for the ordinary differential equations. In the case of ordinary differential equations, we write exponent here. Exponent what was it? I don't hear what you said.
This form
we just substitute the form in which we want to search particular solutions of our equation into the equation. Just want you to recall this part of the theory. So let's do this with our equation. Let's substitute this form into our equation. What we are going to get? Alpha 0 q to the power of n plus 1 plus alpha 1 q to the power of n plus and so on plus alpha k q to which power? N plus 1 minus k is equal to 0. And what's the next step that's done in the theory of ordinary differential equations?
we should somehow
We can divide our equation by this guy. Okay, then what we are going to get if we do so? Correct? Alpha 1 k minus 1 plus and so on plus alpha 0 by 1 equals to 0. The quantity that sits in the left-hand side of this equation is called usually the characteristic polynomial. This is the characteristic polynomial for our difference equation. And we since it should be equal to 0, this is just an algebraic equation for q. And we know from the theory from mathematics, from the theory of algebraic equations, that it has how many roots? How many q values can be found? K roots, exactly k roots. It has exactly k roots but these roots may be maybe complex. These roots may be complex. C. I write letter C to say complex. And they may be different, all different, but some of them may be equal to each other. So it is a repeated root. Okay. So let's try to recall how we define the general solution of the ordinary differential equation if we know these roots. Do you know or do you remember how the general solution is defined? This is just some solution. At every value of q, that is root of this equation, we will get one particular solution, right? But these particular solutions can be combined together. We can form a linear combination, right? And this linear combination will also be a solution of the original equation, or in our case of this difference equation. Okay? So if q with index, some index, if qi is a solution of four stars, then first option, second option. First option, if qi is a simple root of p of q equal to 0, then all other solutions are c constant multiplied by qi at any value of c. Okay? If qi is a root, I don't know English for this Kratnik way, repeated roots, let's call it a repeated root. Do you understand what I mean? So you may have several equal numbers as a root of this equation. For example, if k is equal to 2, we all know that square equations may have two equal roots, right? When the discriminant is 0. So if qi is a repeated root, of I need this word, кратность. I'm sorry, I will look up a word. Кратность корня. Let me check the term. Multiple root, just multiple root. So multiple. If qi is a multiple root of multiplicity mi, m means how many times it was repeated in the solution of the original equation. Okay. Then the solutions will be qi, then n multiplied by qi. Let me check. n, and here I need c, a constant c, which goes from 1 to c m ith minus 1. Let me check. Qi to the power of n, if I'm not mistaken. No, I don't like it. Sorry. Here I should go. Yes. I. And then M. Let me check. So. Yes. Okay. I'm sorry. At this point, it's a little bit different. Not exactly parallel to the case of ordinary differential equations. That's why I'm thinking longer. So it's going to be some constant C1i multiplied by n to the power to 0th power by qi by qi.
So n to the power of I.
And yeah, the general formula will be like this. Yes, you're right. I'm thinking if I should write ith power here, and I think
Yeah, I
I
think there should be n.
here.
And in the first about a simple root, we also should have to the power n. Там, где про простые корни, там тоже степень надо.
No. We just take the root and multiply it by some constant.
Ну, надо общее выражение для n.
Sorry, what did you say?
Там, где для простых корней simple root, we should have q to the power of n also.
No. No, because q is a root of this characteristic equation. N played a role here when we formulated this characteristic equation, and we divided the whole equation by n, q to n plus 1 minus k. And we got the characteristic equation, and then we got its roots. Its roots. And then you can say that q first minus...
No, but when we define the solution for the y. То есть, да, это корень вот этого уравнения, полинома, но общее уравнение у нас получается это решение двоичника.
Okay. Yes, right. Okay, you're right. So here, let's think. So it's gonna be n to 0th power, then n to first power, qi to the power of n, and so on. C to which power? m1 minus 1. Okay? Yeah, it looks like this is true. C.
And between them should be plus.
Well, these are all individual solutions. I'm saying that these are all individual solutions, and we can combine them to form the general solution. We can combine them to form the general solution. Like this, yn is equal to the sum of from I to m1 minus 1 c1 ith by n to the power of I used the letter I for different purpose. Okay. Let me change the index here to avoid misunderstanding. So I, J, K, L, M. Which one do you like the most? J. Did I use J somewhere? J, J, J. Well, I can use J. Okay. Here and here and here. Then I keep this guy. Just 1 to the power of n. Do you like this formula, Alexandra? Plus, and so on. M R minus 1 C R J n to the power of J Q R to the power of n. That's it. R says that we have R roots. Everyone has the multiplicity m j. Okay. Is it clear at this point? Should we stop and discuss it again? This is the general solution. General solution of 4 stars. Okay, no questions? Now, let's formulate the following fact. Since this scheme is linear, and since this scheme 2 stars is linear, if we define the delta as y minus y star, correct. If we define vector delta as the difference between the exact solution of the non-disturbed difference equation and the solution of disturbed difference equation, this whole theory will be true for this delta. Okay? So we can say that delta n satisfies the same equation and characteristic polynomial should be written specifically for delta for sure. Okay? The theory holds true. So, and now we can formulate the theorem. In order for the scheme 2 stars to be zero stable, it is required and sufficient that all roots of P of Q equals 0 for the characteristic equation. That all roots satisfy the following relation or inequality. All roots are less or 0 to unity, and the root with absolute value, I need some number J, has multiplicity of 1. Multiplicity of 1. So let's plot it. This is the real and imaginary parts of our roots. Okay? This theorem says that we need that all these Q values lie within this circle, on the complex plane. And if we have a root that sits on the circle, it should be only 1. It should be alone on that circle. Well, I will not prove this theorem now. Just let us see how it can be used. But is it clear that the importance of this fact? I want you to feel the importance of this fact. So if you are able to prove for the scheme that you developed that for the characteristic polynomial all the roots are below 1, then you can say that your scheme is zero stable. So your scheme preserves at least constant solutions, doesn't let them go away as the time increases, and doesn't let them go away as the time step decreases, which is the most important part.
So, because of this general solution, like because q to the power of n, so if q less than 1, it not goes.
Yes, you can see it from this formula. If q is less than 1, every term in this formula will tend to 0, as n tends to infinity. And n tends to infinity when we take time steps smaller and smaller. If we fix the interval in time that we consider, so t capital is fixed, then n can grow only in the case when you make this tau smaller and smaller, the number of points of our mesh. We'll have more and more points. And this is a good property. Every term tends to 0 here. At least it doesn't grow up infinitely. Okay? In case we have a multiple root, then this n coefficients appears in the formula, right? If the root is simple, not a multiple root, then we don't have this n coefficients because j is 0. Okay? Only j0 term remains in this sum for simple roots. If the root is not simple, then we can allow only for we cannot allow for multiple roots here when q is equal to 1. Why? Because in this case n is present as a multiplier in one of the terms, and when n grows infinitely, this term, this particular term, where q is equal to 0, will grow infinitely as well. Okay, and it will spoil the stability. So actually, we just proved we just proved half of the theorem discussing this formula. The second half, the proof of the second half is a little bit more tricky, but it's sufficient for our understanding. Let's consider. Let's maybe consider an example, or maybe more important at this point to discuss zero stability property for the Runge-Kutta method. Let's check this property for the Runge-Kutta. Delete this. And I will delete this. And this as well. Let's make this theorem number 1. Theorem number 2. Runge-Kutta and k-step linear Adams methods are zero stable. Let's consider only Runge-Kutta for simplicity. So, in case of any Runge-Kutta method, including any Euler method, what did we see? How the left-hand side is looking for Runge-Kutta?
So we need to expand by its
right? So this is the general formula, the final formula of any Runge-Kutta method. And kj's are defined through the other two sets of parameters. Do you remember? But the general formula is like, it looks like this. And here in k, only the right-hand side is involved. The right-hand side that's computed at different points between Tn and Tn plus 1. Okay? So, the left-hand side can be represented, oh, I'm sorry, tau. Tau should sit here in Runge-Kutta method before the sum, and I can put it down here. Right? For the Runge-Kutta method, we only have two terms on the left-hand side. Okay? So, can you tell me what the characteristic equation will look like if we put q to the power of n plus 1 minus q to the power of n, and we say that the right-hand side is 0 for the particular problem that we want to consider, right? When we discuss zero stability, we consider this problem. Oh, sorry, wait. First derivative. Okay? Then, on the right-hand side, we have 0 here. This is our characteristic equation. Okay? Do you agree? So q is equal to 1. Please check the conditions of the theorem number 1. It is okay because we don't have roots below 0, but the only root we have is has multiplicity 1, which is okay in terms of this theorem, and we discussed why. This proves that any Runge-Kutta method is zero stable, or in other words, it's adequate. It's adequate to consider, adequate enough to consider or to work with. If you think about the classical Adams method, in the left-hand side, it also involves only two values of the unknown function, the classical Adams. The classical Adams involves many previous points on the right-hand side. Do you understand what I mean? That's why the classical Adams, in this sense, the proof for the classical Adams is the same or very similar to the proof that we just formulated.
Can you explain once more, Professor? I didn't catch
What do you want me to explain, Charles-Mon?
the equation of the Adams method. What you are talking?
Well, we discussed Adams last time, and last time actually we formulated one example of the Adams method, which was like this.
Yes, I know. Yes,
Okay, so if you put and all we only have two terms on the left hand side.
yes,
Okay, so if you formulate the characteristic equation here, you will have, okay, let's divide by q to the n minus 1. No, I didn't, no, sorry. This was a wrong example, actually. Because this was not an Adams method. It was an example of another two-step method, not Adams family, because it involved yn plus 1 and yn minus 1. All Adams methods involve only these two values on the left-hand side. Okay?
okay.
And if they involve only these two values, you will get, for the characteristic equation, you will get this again. And this equation formally has many roots actually. It has this root, and we can say that it has also n roots that are all equal to 0. And again, the conditions of this theorem are satisfied. Okay?
And the stable equation for zero stable without
The algorithm of the Runge-Kutta method it's not called, it is proven to be zero stable.
I mean that the condition for the condition of stability of numerical method in case of zero stability will be just the norm between y's component equals to 0, not less equal, just equal to 0, because capital K of t it depends on f, but f for zero stable method is 0. В общем, когда на zero stable метод, там для k от t, вот это, которая у нас до этого была, мы считали, что от тау она не должна зависеть, то будет 0.
Different story. Integral exponent, yes, exponent k of t, it is exponent Yes, and you have e to the power of 0. It's unity. It's unity. It's a good challenge question in the end of the first lecture. Yes, sorry that I couldn't answer your question right away, and you answered it actually yourself. So, any other questions at this point? So I just wanted to you to remember that Runge, Kutta, and Adams are zero stable, and thus they are adequate to work with. And nota bene, since I, by mistake, I wrote this method, let's discuss, using my mistake, let's discuss the property of this method. It's a very good example. It's possible to formulate it, it's very easy. All right, it's a two-step method. But what we have for it, q to the power of n plus 1 minus q to the power of n minus 1 is equal to 0. This is the characteristic equation of this method, right? Then I divide everything by this guy, and I get q squared minus 1 equals 0. And I'm sorry, but I have two roots here. Q is equal to plus or minus 1. And
So
it's not zero stable. This guy is not zero stable, so it can lead to the behavior when we expect a constant solution and we get something else. We get something growing with the density of our mesh. We make the mesh denser and denser and observe strange behavior of the solution just because of the property of this method. That's why this particular method is not recommended. It was used back in the days when people did not have computers. Because since they didn't have computers, they could not make the mesh smaller and smaller. They could not take smaller and smaller steps. And they did not observe this kind of behavior just because of the limitations of computational device. Right? In our days, when we have almost infinite capabilities in terms of making tau smaller and smaller, we should be careful with this method. It can lead to oscillatory or even artificially growing solutions. Okay, let's break.